A very good morning, we are from Group 11. So in this project, we are to design a suitable way to produce purified terephthalic acid PTA using a commercial way to maximize the yield and selectivity. So PTA is a purified product with impurities 4-carboxybenzaldehyde, 4-CBA, short form, with these impurities content lesser than 25 ppm. So there are two routes in producing the PTA. The first step is the oxidation of P-silane to produce crude TA and hydrogenation of crude TA to produce purified TA. So in step 2, which is the hydrogenation part, we propose to use a trickle bed reactor, which is also considered a pet bed reactor, because catalyst is being used in this reaction. In the production, so we propose this reactor because TBR is suitable for a multi-phase reaction and it has low energy dissipation rate and high catalyst loading per unit volume, which is commercial for industrial use. And the catalyst proposed to be used is multi-wall carbon nanotubes along with palladium tin, prepared using SI method, which is the successive impregnation method. And this catalyst, it has a SN to PD molar ratio of 0.1. So this bimetallic catalyst prepared using this method is suitable for the hydrogenation because it will produce the impurities of 4-CBA less than 25 ppm, which is 24 ppm. So this is suitable to be used and it will increase the selectivity from initially 5.71 if used without the SN, increase to 16.59 of selectivity with the presence of SN. Therefore, this is the most desirable catalyst for the impurities for CBA hydrogenation that won't cause excessive loss of TA and to give a high selectivity and yield of PTA production. So let us proceed to the calculation now. Our calculation is to calculate the sizing for the reactor, which is to see the most suitable volume, the commercial volume to be used in the industry. So from here, we are using this formula, which is the pet bed reactor formula because catalyst is being used. So we have to calculate the weight of catalyst, which is equal to the volume of reactor. And from the journal, before that we get the delta and the volume expansion equals to 0.5 and 1 respectively. But since this reaction is considered in liquid phase, so we didn't take the volume expansion into account. We just calculate it using the normal liquid phase method without the volume expansion. So from the journal, we take the initial concentration equals to 0.025 m, and we calculate the feed equals to 30,000 ton per year, which is equals to this value in molar flow rate. So after getting the FA node and CA node, we are able to calculate the feed node and insert all these values into the formula. So before inserting into the formula, we get the average rate constant value K from the journal also at 1000 rpm of stirring rate. So we get the K average value, and then we insert into the formula to calculate for the weight of catalyst bed, which is also equal to the volume of pet bed reactor, and then we get 2.89 meter cube for the sizing.
Since we have proposed trickle bed reactor as our most suitable reactor in the process of hydrogenation of crude TA to purified TA, we will look into how this reactor works. In the first process, the dialkyl benzene compound is oxidized to TA by means of two-stage process utilizing certain conditions to obtain TA with improved impurities. We will look into the hydrogenation process now, where the crude TA is dissolved in water under certain temperature and pressure. It is hydrogenated to convert 4-CBA into p-tolic acid. In one constraint, in developing a process for isolating the purified TA from hydrogenated liquor solution in the level of 4-CBA and p-tolic acid, acceptable in the final product, and also this hydrogenation effect the color bodies to become a colorless compound, the crystallization method. This process begins with filtering the dispersion to form a CTA. This CTA filter is then combined with the crystallization solvent at a certain temperature to form a solution. The PTA is then crystallized by reducing the temperature together with the solvent. The last process is separating the crystallized PTA acid from the solution, and the selective crystallization solvent is preferred to be a non-aqueous, non-corrosive, and non-reactive with the TA. And we have proposed N-methyl pyrrolidine as the solvent.
So we move on to our next section, which is that the type separation used to produce purified TA in crystal form. So basically, there are two separation processes that are involved in to produce TA in crystal form. First is evaporation and crystallization. Evaporator is used to convert liquid form of purified terephthalic acid into vapor and to get a more concentrated solid, while crystallizer is to produce crystalline form of PTA and to achieve a liquid-liquid solution. So to propose our project, we decide to use the draft tube baffle crystallizer, which is DTB. So DTB will look like this. This process of crystallizing will start when we enter the DTB from here, and then the impeller pump will exhaust and pump the solution into the evaporator, and with the heat supply, it will evaporate the solution. After a few minutes, the cool solution will be form crystal PTA, and then baffle will distribute the uniform size of crystal and to be obtained in the slurry. So move on. How does this separation system works and the operating conditions involved? The material for the evaporator itself is called Baschuskanzler thin film evaporator. Film evaporator was chosen because its property is very quality, such as operation reliability, high on streamline, constant product quality, long service time, and also it has low maintenance cost. The thin film evaporator will be operated under reduced pressure. Steam heating medium is used to heat the evaporator. The separation is also made in vacuum condition to expand temperature distribution. So after few calculation, the operating condition for the evaporator part for the feed is 3080 kg per hour. The temperature is 267 degrees Celsius, while the steam that provide heat for the evaporating is 100 degrees Celsius and 1 atm. So moving on to the crystallization part in the DTB. So DTB work with low supersaturation. DTB can restricting the growth of crystal. Large crystal commonly be produced by intensive dissolving. So the operating condition we propose for DTB, the crystallization process is 180 and 140 psi. It is also important to control the retention time and crystal mass to achieve effective process control. This can be done by separating crystal from water. TA is continuously crystallized out of the solution, gradually accreting the crystal. So why we choose the DTB crystallizer? There are less problem with incrustation on the wall as the heat is not withdrawn via the wall. DTB also has low temperature rises at low power input. It is also capable of producing large singular crystal. DTB also can be operated at low operating cost.
Strategize how to maximize the production of PTA in the solid form. So there are several methods to maximize it. First, we use the spray reactor, and as we propose in the separation system, we use DTB crystallizer because based on the journal from Mangley 2013, the spray reactor is demonstrated to produce high purity of terephthalic acids, which with the positive A of impurity less than 25 ppm as mentioned in the project. The TPA crystals formed from the spray reactor are white and light-wave particles in the size range of 600 to 1500 micrometer. And this discovery has significant practical implications as it demonstrates that a continuous spray reactor that has the potential to produce polymer-grade TPA, and at the same time it can save the cost of the operating. Next, the effect of liquid volume in developing the crystal form of PTA. Based on our research, a smaller liquid volume can increase the crystal mechanism growth, which we can maintain the concentration of solids, but the liquid volume doesn't affect the crystal size. So here we just focus on the crystal mechanism's growth. Below we can see the graph that the different liquid volume doesn't change the crystal size, but different liquid volume can change the crystal mechanism growth, which less liquid volume can increase the crystal growth. Next, the last strategy we propose is optimizing the crystal temperature in the crystallizer. As stated by Kitty, Supakrampi, Somsompi, Hussein, M.A. and Nausut W, they propose that the temperature optimization is at 400K to 523K, and this can minimize the nucleated crystal, at the same time can maximize the desired crystals form of PTA. So by optimizing the temperature, we can maximize the desired crystals, and we can produce the average size of crystals between the 170 and 190 micrometer respectively. And the quality desirable of crystal can be produced with final batch time of 30 minutes. Next, we proceed to the sample calculation in the evaporator and the crystallization. In the evaporator, we take the data from the journal, which inlet peak temperature is 267 degrees Celsius, and the composition of solid is 0.2, boiling point temperature is 181 degrees Celsius. And then after that, we draw the diagram of the evaporator and we fix the flow rate at 30,000 pounds per year and convert it to kg per hour. And last, we have 2 times with 95 conversion as we proposed in the reaction pipe. After that, we use the mass balance to calculate the L and V. We assume there is no evaporation of water. After that, we take the H and the lambda from the steam table to calculate the steam. The crystallization part, we draw the diagram of the crystallization, and molecular weight of PTA is 166.13 gram per mole and the water is 18.02 gram per mole. The solubility we take from the journal is 0.71 gram terephthalic acid per 100 gram of water at 170 degrees Celsius. And we also assume there is no evaporation of a vapor stream, and we calculate the composition of C and S. After that, we use the mass balance of water balance and solute balance to calculate the C and S. And last, we got S as 1,105 kg per hour and C is 1,354 kg per hour. So, in conclusion, we have the reactor and the separation systems are as proposed in our presentation. This integrated project is therefore ended after a long journey of discussion, work, and cooperation from each member of the group. Overall, from this integrated project, we have learned extra knowledge on the waste in production of purified TA, and we are able to apply the knowledge from the lectures in real-life industrial situation. However, there's still a lot of space of improvement in this project and proposal, as our knowledge is not mature enough in this industry. We hope that there are chances for us to learn more about this production process in the future. Thank you.